Alright, so next exercise 3. Here, just like before, we have an inner product space V, and we are defining a function zeta whose input, as input we have an ordered pair of vectors from V, and that means zeta is a function like this. Its domain is the Cartesian product V times V, and it takes values in the underlying field F, which is either the field of real numbers or the field of complex numbers, because V is an inner product space. And the definition of zeta is this: zeta of u comma v is defined to be the norm of the difference u minus v. Then zeta has these properties. The first one says that zeta always takes non-negative values, and that means in particular that zeta of u comma v, no matter what u and v are, is first of all it's a real number, and then it's not negative, it's a non-negative real number. So actually, even if v is an inner product space over the field of complex numbers, this function in fact is a real valued function. So it only takes non-negative values and is 0 if and only if the two vectors are the same. The second property says that there is a kind of symmetry. It does not matter whether we take u comma v or v comma u, we are going to get the same zeta value. And the third one is triangle inequality, which is this inequality. You can see that it involves three vectors u, v and w coming from capital V. Now you think of the plane of this whiteboard, and you think of 2 points on this plane. We have the notion of distance between these 2 points, ordinary geometric distance, which is the length of this straight line segment joining the 2 points. And this can also be thought of as a function, suppose zeta dash, in which if you give these points some name a and b, then zeta dash calculates the distance between a and b. Then this function zeta dash also has exactly same properties. Let's see how. The distance between 2 points, keep in mind this is actual physical distance, geometric distance, is never a first of all it's a real number, right? And that too, it's never negative, it's always non-negative, and it is 0 if and only if the 2 points actually are the same, that is they are just a single point. Otherwise it's non-zero, it's positive in fact. So that matches precisely with this property, and then it does not matter whether you calculate this distance from a to b or from b to a, you are going to get the same zeta prime value. Okay, and the third one, triangle inequality, in fact comes from this geometric fact about an ordinary plane triangle, and we know that if we take the sum of any two lengths of such a triangle, then that is greater than or equal to the length of the third side. Okay, and in fact equality occurs only when the triangle is degenerate, meaning that the three vertices are collinear, that its area is 0, and in that case the three sides are just this. One of them is this, the other one is this, and the third side is this thing, the larger one, between these two vertices. So here you can see that the sum of the lengths of this side and this side is precisely equal to the length of this side. Okay, so because of this exactly similar properties, This function zeta also is said to give the distance between two vectors u and v. It's just because of that analogy. Do not attach any more meaning to this word distance. It's distance in the sense that similar properties are true. Okay, and those of you, and I mean most of you who know about metrics will recognize this thing. I mean all these things as this, that this is a metric space. Where the set of points is the set of vectors v and the metric is zeta. Okay, so let's now solve this. If you think about it, sometimes it may feel strange that calling such a value distance, but it's distance in the sense that the ordinary distance function, which allows us to calculate distance between 2 points on a plane or say in 3D space, also is a function like this. So if we can call this one distance, why not call similar functions also distance function? Okay, solution. So it's pretty computational. We just apply the definition and that will get us the solution. Part A. We just first apply the definition. Zeta of u comma v is the norm of u minus v, but we know what this thing is in terms of inner product. It is the non-negative square root of the inner product of u minus v and u minus v. And from inner product axioms, we know that this inner product is a non-negative real number. That means it's greater than or equal to 0. So its non-negative square root is also a non-negative real number. So from there we are getting this inequality. Okay, so this one. Also, from another property of inner products, or from another axiom in the definition of an inner product, this is equal to 0 if and only if u minus v is equal to 0. That is, the inner product of a vector with itself is 0 if and only if the vector itself is the 0 vector. If and only if u is equal to v. Hence, if and only if u is equal to v. So that's how we have part A. Then part B, that is, the zeta value does not depend on the order in which the vectors are considered. And here we are going to use that result. It's the corollary to lemma 441. That result just says this, that if in an inner product space you have a vector x, say, and a scalar alpha, and you consider this multiple alpha x, then its norm is equal to the absolute value of alpha times the norm of x. We have already seen this thing, we have proved it also. So we are going to use this thing here. By the corollary to lemma 441. So let's start with this. Zeta of u comma v is equal to, by definition, this. But now the vector u minus v can be written like this. Minus 1 times v minus u. Keep in mind that this is equal to this, and that follows from the ordinary vector space properties, okay? And in this very next step we are using that result. That is, this will be equal to the absolute value of minus 1 times the norm or length of v minus u. So that is nothing but this. So that's how we have part B. And next, part C. To establish part C, we calculate the square of this zeta of u comma v. We have this square equal to this by definition. Okay. Now it is this. Now we know a property of or it comes from the axioms in the definition of an inner product, that this inner product, not the square root, not the square, but only the inner product value, because the vectors are the same, is a non-negative real number. So if we lift square and square root, if we cancel them out, then we can in fact just simply write this, because this value is non-negative. But we will need this, and since it's non-negative, it's also equal to its own absolute value. Okay, so that's why we are writing absolute value. We will see why we need absolute value. Alright, so now we are going to introduce that third vector w, like this: u minus w plus w minus v, comma, here also we are going to do the same, u minus w plus w minus v. And now what you do, in the next line you expand this inner product, so to speak, using linearity, and in fact using whatever we got before, and that will get you this, the inner product of u minus w. And in doing so, what we are going to do, we are going to interpret this as the sum of two vectors. One of them is u minus w and the other one is w minus v. So then, doing that thing, that expansion, we get the inner product of u minus w and u minus w plus the inner product of u minus w and w minus v. Like that we will have the inner products 4 of them we will get. Plus u minus w and w minus v. Plus the inner product of w minus v and u minus w. And finally, the inner product of w minus v and w minus v. And now in the next step we use triangle inequality. But triangle inequality of in the system of real numbers or complex numbers, in fact, actually, because we know that these inner products, well, not this one, but this one may in general be a complex number. But there also we have the ordinary triangle inequality. So its extended version we can use and write next this. That is, with the inner products, we individually we take absolute value. Plus w minus v comma u minus w, and finally w minus v comma w minus v. Okay. Now whatever we did here, we can do its opposite here. That is, we can take square root and write square. If we do all those things, we will get this naturally. The norm of u minus w square, which is this thing, plus, well, there is no need to write in this short space, we can write in the next line, u minus w comma w minus v plus w minus v comma u minus w plus. So here also, because the vectors are the same, this will be the square of the norm of w minus v. Okay. Now we are going to use Schwarz inequality. So we have to recall that. For these middle terms, this one and this one. So using that inequality, we are going to get this. Plus, let me first write it and then I will explain. And we can recall that result. Schwarz inequality was theorem 441. But let's recall Schwarz inequality. Okay. That thing says that in an inner product space, if you have two vectors x and y, say, then the absolute value of their inner product is less than or equal to the product of their norms. That's what we have used here. We have replaced the absolute value of this inner product by the product of the norm of u minus w and w minus v. Here the order is the opposite, but after all we are going to get the same thing. This one is less than or equal to the length of w minus v times the length of u minus w. And this, if you remember, is in some way related to the Heisenberg's uncertainty principle in quantum mechanics. Okay, so now you look at this thing. Square of a real number plus square of another real number plus 2 times their product. So that means this is a perfect square. But because we ultimately want things in terms of zeta, so let's write like this. That is, what we ended up showing is this. The square of the zeta value of u comma v is less than or equal to, because the inequalities are in that direction, this. And now keep in mind that these zeta values themselves are real numbers, okay, and that too not just any real numbers but non-negative real numbers, which is why we can lift squares from both sides. That is, to say it more casually and non-rigorously, we can take square root on both sides. So in the next line we write this, since and these are all non-negative, the above inequality implies this. W comma v. So that's how we have our triangle inequality, and here the solution ends. Now let's see the next exercise. Exercise 4. If a set of vectors is given w1, w2 and so on up to a finite set, this is an orthonormal set of vectors in an inner product space V. Prove that the sum of the squares of these inner product values of V with all the wi's is less than or equal to the square of the norm of the vector v for all v in v. And this inequality has a name also. It's Bessel inequality. Am I getting the spelling correct? Yes. And this Bessel, I believe it's that Bessel after whom that Bessel functions are named in differential equations. Okay, so let's see the solution. Consider the vector. We are now going to consider a vector that is from V. Let me first write it and then I will say what it means in a sense. Consider the vector U equal to V. Okay, so V is our any vector coming from the inner product space V, capital V. From V, what we do, we subtract the components of this vector V itself from V along the directions of these other vectors, the Wi's. The component of V along W1, for example, is this inner product times W1. Similarly, the component of V along W2 is this, and like that this. Now we know something about this type of vector U, namely from a previous result that if we remove the component, it's like this, no? And I remember that in trying to interpret this, I messed up in one of the previous videos. It's like this. You have one vector, you are decomposing it into some components so that the sum of those components is the vector itself. Now, if you remove those components from the vector, for example, say you have a 3D vector which is emanating from the origin like this. It has its I component along the positive x-axis, j component along the positive y-axis, and k component along the positive z-axis. Now, if you remove, for example, the I component of this vector from this vector, and also the j component of this vector from this vector, then the vector does not stay this, but it becomes this, which equals the component that the original vector has along the z-axis. But then this becomes perpendicular or orthogonal to these other vectors I cap, j cap. In that sense, this U is going to be orthogonal to all the Wi's, and this is in fact the result that we have seen in lemma 445. Then from lemma 445, this U is going to be orthogonal to all the Wi's. Okay, so if that way you interpret, then it's really not difficult to remember these things. Now what we do, now we calculate the, what I'm trying to say is that we are now going to calculate the inner product of V with itself, because that inner product will be equal to this. So let's see what we get. And in fact, let's just start with this. So this by definition, because the square root will not be there because of this square, is just the inner product of V with itself. But we can write V in terms of U and this linear combination in this way. Of course, I won't be able to write it in one line. So it will be, let me, okay, and one more thing is that the author has written Wi, but we can write it like this also. So V comma W1 plus, not writing W2, that would take some space, plus let me write the final one, V comma Wm times Wm plus U. But not just in one line, I am not even able to write it in one side. So let's continue from there. Its inner product with itself. That is plus U. Alright, so let us now use that result by which we expand this inner product. That is what, oh, and in that expansion, of course, all the possible products are going to come, but things will reduce to more simpler forms because the set Wi is orthonormal. So for example, what I am trying to say here is that in calculating this inner product, when you consider the inner product of this vector and this, the same thing, then what will you have? This times not this but its complex conjugate times, because these are scalars, times the inner product of W1 with W1. Right, so that's how things are going to come. And then when you take the inner product of this with the next vector, say W2, you then get this. No? But because our set Wi is orthonormal, since it's orthogonal, these inner products where the Wi and Wj are different are all going to be 0. So we need not bother about such terms. And the ones that are going to come after this, also for this term and the other terms on this side are going to be 0. Only this term survives. And because of normality, the length of W1 is 1, and as such this inner product value is 1. So we are only left with this or this. Okay, and this is going to happen for all the terms. So I hope you get my point. That's because once you do all these things, this expansion for only this vector, you will then have similar expansions for the other terms in this sum, right? And for them also using orthonormality of the set Wi. For example, the terms, the sum that is going to come for the next term actually ultimately will give us this. So that's how we are going to get such squares. How many of them? M number of them. So you can write that like this thing. V comma wy square, where I varies from 1 to m. Okay, but not just that, you are also going to have in fact I forgot to mention it, while writing the terms that are going to come for this term, by taking its product with all the terms here, we are also going to encounter this. Right? This times that that last vector. But because of these things, this is also not going to survive, and we indeed have only this. But there is one more term that is going to come and which will stay, is the inner product of u with itself, because we were considering all possible products. So that term survives. Okay. So that's how we finally, in fact this is not greater than or less than or anything, but this is in fact exactly equal to this plus this. However, since this is a single vector, not two different vectors but u and u, so from properties of inner product we know that this is a non-negative real number. And as such, if we don't write this, then likely we are writing less. So that's why this is greater than or equal to this. If you, well, in the original exercise you have wy here and v here, but that does not matter. You can write that also in place of this. Why, that I leave to you, up to you to understand. Okay, it's a simple matter. So that's how you have Bessel inequality. And let me just end the video here itself. In the next vector space update, we are going to solve the other exercises that come after this. And tomorrow we have again our upload, and tomorrow let's solve algebra exercises from Lee. So with that, that's just it for tonight. So see you tomorrow with Lee's exercises and solutions of them. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.